Hello friends, today we have come up with an interesting chapter that is surface chemistry. Surface chemistry is very important chapter and to learn this chapter we come up with some definition which we need to learn and these are as adsorption, the accumulation of molecular species at the surface rather than the bulk of the solid or liquid is called adsorption. Adsorbate, the molecular species or substance which accumulate at the surface. Adsorbent, the surface of material on which adsorption take place. So adsorbent is the surface on which adsorbate accumulates, and this process of accumulation is called adsorption. Desorption, the process of removing the adsorbed substances from the surface on which it is adsorbed. Absorption, when the molecular species or substance enter in the bulk phase in solid or liquid is called as absorption. The difference between these two terms, adsorption and absorption, is only of the letter D and B at second place. That is adsorption and absorption. So keep it in mind. Sorption, when both adsorption and absorption take place simultaneously is called as sorption. Mechanism of adsorption. Inside the adsorbent in bulk, the forces acting between the particles are mutually balanced, but on the surface, the particles are not surrounded by atoms or molecules of their kind on all sides, and hence they possess attraction forces. So, particles stick on the surface of the particle stick on the surface of the adsorbent. The extent of adsorption increases with increase in surface area per unit mass of the adsorbent at a given temperature and pressure. Heat of adsorption. With increase in heat, adsorption process decreases. Adsorption equilibrium, as the molecules of the adsorbate are held on the surface of the solid adsorbent, entropy decreases, that is del S is negative. So del G is equal to del H minus T del S. For the process of adsorption to occur, del G must be negative, which is possible only when del S keeps on decreasing and T del S keeps on increasing till ultimately del H becomes equal to T del S, so that T delta G is equal to 0. This state is called adsorption equilibrium. Types of adsorption. There are two types of adsorption: physical adsorption or physisorption. If accumulation of gas on the surface of solid occurs on account of weak van der Waals forces is called physical adsorption. Chemical adsorption or chemosorption, when gas molecules or atoms are held to the surface solid by chemical bonds, the adsorption is called chemical adsorption. Characteristics of physical adsorption or physisorption. First, lack of specificity. A given surface of an adsorbent does not show any preference for a particular gas, as the van der Waals forces are universal. Nature of adsorbate. The amount of gas adsorbed by a solid depends on the nature of the gas. Third, reversible nature. Physisorption is reversible because adsorbate may be removed by decreasing pressure. Fourth, surface area of adsorbent. Physisorption increases with increase in surface area. Enthalpy of adsorption. Physical adsorption is exothermic process, but its enthalpy of adsorption is low, that is 20 to 40 kilojoule per mole. Characteristics of chemical adsorption or chemosorption. First, high specificity. It is high specific because it occurs if there is some possibility of chemical bonding. Irreversibility. A chemisorption involves compound formation, so it is usually irreversible process. Temperature. Chemisorption increases with increase in temperature. After saturation starts decreases. Pressure. It is also increased with increase in pressure. Surface area. Chemisorption increases with increase in surface area. Enthalpy of adsorption. Enthalpy of chemisorption is high, that is 80 to 240 kilojoule per mole, as it involves chemical bond formation. Adsorption isotherm. The variation in the amount of gas adsorbed by the adsorbent with pressure at constant temperature can be expressed by mean of a curved temperature as adsorption isotherm. Freundlich adsorption isotherm. Freundlich adsorption isotherm is given by Freundlich in 1909. Gave an empirical relationship between the quantity of gas adsorbed by unit mass of solid adsorbent and pressure at a particular temperature. The relationship can be expressed by following equation, that is x by m is equal to k into P1 divided by n, where n is greater than 1. When x is the mass of gas adsorbed on the m mass of adsorbent at pressure P, k and n are constant, which depends on the nature of the adsorbent and gas at a particular temperature. Relationships given by curve x divided by m on y-axis and p on x-axis. So, Freundlich isotherm gives the reaction as the temperature decreases, the graph moves upward on y-axis, and you can see this graph at our website www.chemistrynotesinfo.com. The curve indicates that at a fixed pressure there is decrease in physical adsorption with increase of temperature. Taking logarithm of equation first, that is x by m is equal to k into P1 by n, we get log x by m is equal to log k plus 1 by n log p. The validity of Freundlich isotherm can be verified by plotting log x by m on y-axis and log p on x-axis. It comes to be a straight line. When 1 by n is equal to 0 and x by m is equal to constant, the adsorption is independent of pressure. Also, when 1 by n is equal to 1 and x by m is equal to kp, that is x by m is directly proportional to p, the adsorption varies directly with pressure. Adsorption from solution phase. Solids can adsorb solutes from solutions also. Example, litmus solution when shaken with charcoal becomes colorless. Factor affecting
adsorption from solution phase. The extent of adsorption decreases with increase of temperature. The extent of adsorption increase with increase in temperature of surface area of the adsorbent. The extent of adsorption increase with an increase of surface area of the adsorbent. The extent of adsorption depends upon the concentration of the solute in the solution. The extent of adsorption depends upon the nature of the adsorbent and adsorbate. Application of adsorption: production of high vacuum gas masks, control of humidity, removal of coloring matter from solution, separation of inert gases, froth flotation process, chromatographic analysis. Catalysis. Berzelius suggests that the term catalyst substance which alter change the rate of a chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalyst, and the phenomena is known as catalysis. I repeat, Berzelius suggests the term catalyst. Substances which alter change the rate of a chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalyst, and phenomena is known as catalysis. Promoter: substances that enhance, increase the activity of catalyst. Poisons: it decreases the activity of catalyst. Homogeneous catalysis: when the reactants and the catalyst are in the same phase, that is liquid or gas. Example: 2SO2 in gas phase plus O2 in gas phase and NO as a catalyst in gas phase gives 2SO3 in gas phase. Another example is C12H22O11 in aqueous phase plus H2O in liquid phase and H2SO4 in liquid phase gives C6H12O6 in aqueous phase plus C6H12O6 in aqueous phase, and these all things, that is reactants, products and catalyst, are in the same phase. So these types of reactions or these types of catalysis reactions are known as homogeneous catalysis. Heterogeneous catalysis: when catalytic process in which the reactant and the catalyst are in different phase is known as heterogeneous catalyst. Example: 2SO2 in gaseous phase plus platinum in solid phase gives 2SO3 in gas phase. Here platinum, that is catalyst, is in solid phase and reactant SO2 is in gaseous phase. So these types of reactions are known as heterogeneous catalysis reactions. Another example is vegetable oil in liquid phase plus H2 hydrogen in gaseous phase and nickel as a catalyst in solid phase gives vegetable ghee in solid phase. Safe selective catalysis by zeolite: the catalytic reaction that depends upon the pore structure of the catalyst and the size of the reactant and product molecules is called as safe selective catalysis.
Zeolite is good safe selective catalyst because of their honeycomb-like structure. They are microporous aluminosilicates with three-dimensional network of silicates in which some silicon molecule atoms is replaced by aluminum atom, giving ALOSI framework. An important zeolite catalyst used in petroleum industry is ZSMS catalyst. ZSMS converts directly alcohol into gasoline, petrol by dehydrating them to give a mixture of hydrocarbons. Enzyme catalyst. Enzymes are complex nitrogenous organic compounds which are produced by living plants and animals, works as a catalyst in many life processes termed as biochemical catalysts. Enzymes and phenomena is known as biochemical catalysis. Example: C6H12O6 in aqueous phase plus Zymes as catalyst gives C2H5OH in aqueous phase plus 2CO2. Another example is NH2CONH2 in aqueous phase plus H2O in liquid phase, and urease as catalyst or enzyme gives NH3 in gas phase plus CO2 in gas phase. Characteristics of enzyme catalysis: most highly efficient. One molecule of enzyme may transform 1 million molecules of reactant per minute. Means they are most highly efficient. Highly specific nature. Each enzyme is specific for a given reaction. Highly active under optimum temperature. The rate of an enzyme reaction is maximum at definite temperature called optimum temperature, and that is about 298 Kelvin to 310 Kelvin. Highly active under optimum pH. Rate of enzyme reactions is maximum at optimum pH, that is about 5 to 7 pH. Increasing activity in presence of activators or coenzymes. The enzymatic activity in presence of certain substances called coenzymes, vitamins, and activators are generally Na plus, CO2 plus, Mn2 plus, Cu2 plus, etc. Inhibitor and poisons decrease or stop the rate of enzyme reactions. Mechanism of enzyme catalysts. There are number of cavities present on the surface of colloidal particles of enzymes. The molecules of the reactant substrate which have complementary shape fit into these cavities, just like a key fits into a lock. On the account of the presence of active groups, an activated complex is formed which then decompose as to yield the products. Colloidal. A colloidal is a heterogeneous system in which one substance is dispersed or dispersed phase as very fine particles in another substance called dispersion medium. Colloidal particles are larger than simple molecules but smaller enough to remain suspended. Their range of diameter is between 1 to 1000 nanometer. Classification of colloids. On the basis of physical state of dispersed phase and dispersion medium. Second classification is on the basis of nature of interaction between the dispersed phase and dispersion medium. Third classification is on the basis of types of particles of dispersed phase. First we take classification based on physical state of dispersed phase and dispersion medium. So dispersed phase is solid, dispersion medium is solid, then types of colloids is solid sol. Example, some colored glasses. Dispersed phase is solid and dispersion medium is liquid. Then types of colloids are called as sol. Example, paints. If dispersed phase is solid and dispersion medium is gas, then types of colloids is called aerosol. Example, smoke, dust. If dispersed phase is liquid and dispersion medium is solid, then types of colloid is called gel. Example: cheese, jellies. If dispersed phase is liquid and dispersion medium is liquid, then types of colloids is called emulsion. Example: milk, hair, cream, etc. Dispersed phase is liquid and dispersion medium is gas, then types of colloid is called aerosol. Example: fog, mist. If dispersed phase is gas and dispersion medium is solid, then types of colloids is called solid sol. Example: pumice, stone. If dispersed phase is gas and dispersion medium is liquid, then types of colloids is called foam. Example: froth, whipped cream. Second classification is classification based on nature of interaction between dispersion phase and dispersion medium. In it, colloidal state sols are divided into two categories. First is lyophilic, solvent attractive. Second is lyophobic, solvent repelling. First we study about lyophilic colloids. The word lyophilic means liquid loving. Colloidal sols directly formed by mixing substances like gum, gelatin, starch, rubber, etc. with a suitable liquid dispersion medium are called lyophilic sol. These sols are called reversible sols. Second is lyophobic colloids. These words lyophobic means liquid hating substance like metals, their sulfides, etc. when simply mixed with the dispersion medium do not form the colloidal sol. Their colloidal sols can be prepared by only special methods. Such sols are called lyophobic sols. These sols are also called as irreversible sols. Another classification is classification based on the type of particles of dispersed phase. In it, colloids are classified as multimolecular, macromolecular, and associated colloids. First is multimolecular colloids. On dissolution, a large number of substances aggregate together to form species having size in the colloidal range of diameter about lesser than 1 nanometer. The species thus formed are called multimolecular colloids. Second is macromolecular colloids. Macromolecules in suitable macromolecule moles in suitable solvents form solution in which the size of macromolecules may be in colloidal range. Such systems are called macromolecular colloids. Another is associated colloids, micelles. These are some substances which at concentration behave as a normal strong electrolyte but at higher concentration exhibit colloidal behavior due to the formation of aggregates. The aggregate particles thus formed are called micelles or associated colloids. The formation of micelles take place only above a particular temperature called Kraft temperature and above a particular concentration called critical concentration. Mechanism of micelles formation. Soap is the sodium or potassium salt of higher fatty acids and may be represented as RCOO- Na. Example: sodium stearate, CH3CH2, COO minus Na plus. When dissolved into RCO minus and Na plus ions, the RCO minus ion consists of two parts, a long hydrocarbon chain, also called non-polar tail, which is hydrophobic water repelling, and a polar group CO minus polar head, which is hydrophilic water loving. But at critical micelle concentration, the anions are pulled into the bulk of the solution and aggregates to form a spherical shape with their hydrocarbon chain pointing towards the center of the shape, with COO minus part remaining outward on the surface of the sphere. An aggregate thus formed is known as ionic micelles. Cleansing action of soap. The soap molecules in such a way that hydrophobic part of the stearate ions is in oil droplet and hydrophobic part projects out of the grease droplet like the bristles hairs. Since the polar group can interact with water, the oil droplet surrounded by stearate ions is now pulled in water and removed from the dirty surface. Thus, soap help in emulsification and washing away of oils and fats. Preparation of colloids. First is chemical methods. Colloids solution can be prepared by chemical reaction leading to formation of molecules by double decomposition, oxidation, reduction, or hydrolysis. These molecules then aggregate leading to form sols. Example: As2O3 plus 3H2S on double decomposition gives As2S3 sol plus 3H2O. Electrical disintegration or Brady's arc method. This process involves dispersion well as condensations. Colloidal sol of metals such as gold, silver, etc. can be prepared by this method. In this method, electric arc is struck between electrodes of metal immersed in the dispersion medium of intense heat produced vaporized of metals, which when condensed to form particles of colloidal size. Peptidization. It is defined as the process of converting a precipitate into colloidal sol by shaking it with dispersion medium in the presence of a small amount of electrolyte. The electrolyte used for this purpose is called peptizing agent. During peptidization, the particulate adsorbs the one of the ion of the electrolyte on its surface. This causes the development of positive charge on precipitate, which ultimately break up into small particles of the size of a colloid. Purification of colloidal solution. The process used for reducing the amount of impurities to a requisite minimum is known as purification of colloidal solution. It is carried out by following methods. First, dialysis. Dialysis is a process of removing a dissolved substance from a colloidal solution by means of diffusion through a suitable membrane. Since particles, ions, or smaller molecules in a true solution can pass through an animal membrane, bladder, or parchment paper or colloidal particles
The molecules and ions diffuse through membrane into the outer water and pure colloidal solution to left behind. Second is electrodialysis. The process of dialysis is quite slow. It can be made faster by applying an electric field. Electrodes are fitted in the compartment. The ions present in the colloidal solution migrate out to the oppositively charged to the electrode. Third is ultrafiltration. In these methods, special filters are used which are permeable to all substances except the colloidal particles. An ultrafilter paper may be prepared by soaking the filter paper in a colloidal solution, hardening by formaldehyde and then finally drying it. Thus, by using ultrafilter paper, the colloidal particles are separated from rest of the materials. The colloidal particles left on the ultrafilter paper are they stirred with fresh dispersion medium solvent to get a pure colloidal solution. Properties of colloidal solution. First is colligative properties. The values of colligative properties, osmotic pressure, lowering in vapor pressure, depression in freezing point, elevation in boiling point, are of small order as compared to values shown by true solution at same concentration. Second is Tyndall effect. It may it is may be defined as the scattering of light by the colloidal particles present in the colloidal solution. Color. The color of the colloidal solution depends on the wavelength of the light scattered by the dispersed particles. The wavelength of light further depends on the size and the nature of the particles. Brownian movement. It may be defined as continuous zigzag movement of the colloidal particles in a colloidal solution is known as Brownian movement. Fifth, charge as colloidal particles. Charge as colloidal particles always carry is electric charge. The nature of this charge is the same on all the particles in a given colloidal solution and may be either positive or negative. Example, positive charged solution, hemoglobin, hydrated metallic oxides. Example, As2 S3 dot XH2O. Negative charged solution, first metals. Example, Cu, Ag, Au. Metallic sulfides. Example, As2 S3, Sb2 S3, CDS solutions. Sixth is electrophoresis. The movement of colloidal particles under the influence of an electric field is called electrophoresis. Negative charged particles move towards cathode and positive charged particles move towards anode. Coagulation. The process of setting of colloidal particles is called coagulation or precipitation of the sol. The coagulation of the lyophobic sol can be carried out in the following ways. First, by electrophoresis, the colloidal particles moves towards positively charged electrodes, get discharged and precipitate by mixing two positively charged sols. The positively charged sol, when mixed almost equal proportional, neutralize each other, then changed and get partially or completely precipitated by boiling. When a sol is boiled, the adsorption layer is disturbed due to increased collision with the molecules of the dispersion medium. This reduces the charge
on the particles and ultimately led to setting down in the form of a precipitate by persistent dialysis. On prolonged dialysis, traces of the electrolyte present in the soul are removed almost completely. Colloidal colloids becomes unstable and ultimately coagulate by adding of electrolyte. When excess of electrolyte is added to the colloidal particles, when excess of electrolyte is added, the colloidal particles precipitates. The reason is that colloids interacts with the ions carrying charge opposite to the that present on themselves. This cause neutralization leading to their coagulation. Coagulation of lyophilic soils. There are two factors which are responsible for stability of or the lyophilic soils. These factors are cha- change and salvation of the colloidal particles. When these two factors are removed, the lyophilic soil can be coagulated. This is done by adding an electrolyte or by adding a suitable solvent. Protection of colloids. Lyophilic soil are more stable than lyophobic soils. Lyophilic colloids have sorry, just give me time. I am get disturbed by someone, my child. Okay, where we are? We are on. Okay, we are on by adding of electrolyte. When excess of electrolyte is added to the colloidal particles precipitate, the reason is that colloids interacts with ions carrying charge opposite to that present on themselves. This causes neutralization leading to the coagulation. Second is coagulation of lyophilic soils. There are two factors which are responsible for stability or the lyophilic soils. These factors are charge and the salvation of colloidal particles. When these two factors are removed, the lyophilic soil can be coagulated. This is done by adding an electrolyte or by adding a suitable solvent. Protection of colloids. Lyophilic soil are more stable than lyophobic soil. Lyophilic colloids have a unique property of protecting lyophobic colloids. When a lyophilic soil is added to lyophobic soil, the lyophilic particles colloids covering up the particles of lyophobic soil. Emulsions. An emulsion is a colloidal dispersion in which both the dispersion medium and dispersion phase are liquid. Generally, one of the two liquid is water, and there are two types of emulsion: oil dispersed in water or O slash W type, and second is water dispersed in oil W slash O type. First, O slash W type. Water act as dispersion medium. Example, milk and vanishing cream. Second, W slash O type. Oil act as dispersion medium. Example, butter and cream. Colloids around us. Most of the substances all we come across in our daily life are colloids. For example, metals, clothes, wooden furniture, houses, newspaper are largely composed of colloids. Application of colloid. Colloids are widely used in an industrial sector. Example: electroprecipitation of smoke. The smoke before it comes out from the chimney is led through a chamber containing plates having a charge opposite to that carried by smoke particles. The particles, on coming in contact with these plates, lose their charge, get precipitate. The particles thus settle down on the floor of the chamber. The precipitate is called Cottrell precipitator. Purification of drinking water. Alum is added to water that contains impurities. To coagulate these suspended impurities, make water fit for colloidal in nature. Example: argyrol is silver sol is used as an eye lotion. Medicines. Most of the medicine are colloidal in nature. Example: argyrol is a silver sol used as an eye lotion. Tanning. Why when a hide animal skin which has positive charge particles is soaked in tanning, or chromium salt which contains negative charge particles mutually coagulation take place. This result in the hardening of leather. This process is called as tanning. Photographic plates and films. Photographic plate and films are prepared by coating an emulsion of the light sensitive silver bromide in gelatin over glass plates or celluloid films. Rubber industry. Latex is a colloidal solution of rubber particles which are negatively charged. Rubber is obtained by coagulation of latex. Industrial products, paints, inks, synthetic plastics, rubber, cement, graphite, lubricant, etc. are all colloidal solution. Thank you to listening this podcast. This podcast is brought to you by Chemistry Notes Info. You can get PDF notes of this chapter from our website www.chemistrynotesinfo.com. You can also join our Telegram channel and get PDF notes and participate in quiz competitions. To join our chemistry channel, visit at Telegram app and search for @chemistry notes info. Thank you to listening this podcast.